All right. So you did the derivative. So tell me what you got again. ln x
So yeah, ln x
plus 1. I agree. Okay, so we do the product rule on that, and we get this for the derivative. The minimum value attained by f. So what are they asking? But what kind of a minimum? We have a couple different types of minimum. Global and local. This one is global. The minimum value attained by this function. Notice there's no endpoints. Global max min is endpoints, derivative is 0, derivative is undefined. Now, the derivative is undefined when x is negative. You can't have a negative, you can't have 0, but then again, so is the original, so we don't have to worry about that. We don't have to treat that as anything in our looking for a max, because you can't have a max or a minimum where the function isn't even defined. And so the derivative is undefined the same place as the original is, and that happens often. All right, so really it's just where does this equal 0? So it's ln x equals -1. This is no calculator, so what do we do from here? So x would equal e to the -1, which is 1 over e. And so most people would circle 1 over e and away they'd go. And that would be a problem. That would be a problem. Now it's a one candidate problem. Global max min usually means list of candidates, but with one candidate, number line could work, right? Number line could work. Now, let's talk about multiple choice questions here a minute. You don't have to justify your multiple choice answers. Now, I think during this review we should, because that's what we're doing. We want to review the process of how we do these problems. But if you were taking the actual test and you had some time pressure, you know, you might be able to skip some of this, but then you got to be careful because one of the choices is no minimum. Maybe this is a maximum. You know what I mean? So you in this one, you would probably not want to skip over it. Now, what's a number littler than 1 over e? 0. Unfortunately, we can't plug a 0 into natural log. 0.1, but 0.1 is not a lot of fun to plug into ln x. Now, maybe if you know the ln x graph, this is the ln x graph right here, and it crosses at 1. Now, 1 over e is like 1 over 2.7 something, right? So that's about 0.3, 0.4, somewhere in there. It's kind of like 1/3, almost. So 0.3 somewhere. So 0.1 I think would work. But here would be, we've talked about this with fractions, and how can you make a fraction smaller? You could multiply the bottom by 2. Doesn't that make the fraction smaller if you make the bottom bigger? Okay. So that would be something you could do as well. Now 0.1 would be okay. All right. But here's how you could use this. So 1 over 2e, that's the same as 2e to the -1. Right? Now plug that into natural log. Natural log of 2e to the -1. Now what do we know about log problems? Well, okay, what else do we know about log problems? Remember, we can bring this power down in front. Okay, now to be honest, well, yeah, no, so you could bring that negative down in front. We'd have negative ln of 2e, right? ln of 2e is a positive, right? Because this is 1, we know 2e is like 4 something, or 5 point whatever. So that's going to give us a positive value if you know the natural log graph. So this negative here tells us that's going to be negative. Or like you say, 0.1. Here's the problem with 0.1. You put 0.1 in, you get a negative, but how negative is it? Because you got to add it to 1. You don't really know what it is, right? And we got to plug it into +1. Okay? On this one, it's not as much of an issue. Okay? All right. What would be bigger than 1 over e? Well, yeah, you could just do e. That'd be easier. E. 2 over e would be a good one too, but we could just do e. Okay? Well, ln e is 1. 1 plus 1 is 2. That's definitely positive. So we do get a minimum, at least. But again, this is not the answer. Why? No, it's not e. It's not e either. No, it's not that. No, what? Read the question again.
Minimum value attained by f.
So what's that mean?
So you have to plug that back into the original.
They want the y value of the minimum. Okay? This is where the minimum is at 1 over e. So we did everything right. 1 over e is where the minimum is, but what we have to do is go back to the original. So 1 over x, or excuse me. So x, so we plug in a 1 over e for x, and then times ln 1 over e. Well, what's ln 1 over e? That's ln e to the negative 1. That bring the negative 1 down. What's ln e? 1. So bring the negative 1 down. So it's negative 1 times 1 over e. So it's A. Choice A. So that's a tricky one. You're right. And multiple choice will do that. We haven't run into a lot of them, but you'll work the problem along, and then you think you got it because you see the answer, but you got to be careful because they'll throw that in there. All right.
25.
Geez, I tell you, I have never had two classes so polar opposite. Carly must have thought she was in the Twilight Zone this morning, being in that other class.
Why? Because they don't ask questions?
God, I asked, I said, okay, what, I know, that's what I'm saying. I'm saying, hey, exam 2, yeah, I was going to say, Roland wouldn't have a single packet problem done. No, I say, come on, let's do, and I don't know, they're all just afraid that they're asking a stupid question or something. Nobody will ask.
I don't understand how you switch over from 1A and 1B to this.
Just go the entire package.
How?
Oh, yeah, so
How?
Carly really thought, Carly might have thought she was in the Twilight Zone sitting in my second block, but Tiana sat in my Algebra 1B class this morning,
1A
first
and
1A and 1B. That really seemed like the Twilight Zone. Wait.
It was great.
Was it terrible?
I mean, I can comprehend that, but
Oh my God.
people in there, some of those
We should
conversations
take that
were like
test and they should have arts.
hallway conversations.
Yeah.
Can you take this?
Mix up those tests.
I learned a lot about how much pencils and tattoo fees cost.
Oh, is that right?
Yeah, these little side conversations that were happening. Pretty good.
All right. What one? 20 what? 5?
25.
25.
All right. So anyway, in their class, I said, well, come on, are you sure I'll work some? So I picked a couple myself, and you guys, you
Make
just
them
know. Well, here, the next one. What, another one? Oh yeah, how about the next one?
Make them suffer. Don't
I think
push
I've
them.
done every one of them so far. All right. Suppose that g is a function defined for all real numbers. Which of the following conditions assures that g has an inverse? Okay. There's two things you have to do to answer this. Number one, you better understand what would assure that g has an inverse function. So let's think.
What does
Yeah.
that mean?
Well, let's talk. Here's a function.
First, we should just look at real numbers.
I was thinking like arc sine. Is that way off?
Kind of.
Nope.
Arc sine is an inverse function. It's the inverse of sine. Now, well, it wouldn't be a bad one to think about because we have to do something special to the sine graph to do its inverse. Because what would the inverse of arc sine look like? If I was going to graph it,
Up forward.
it would go up and like this.
Something.
Is that a function?
No.
Vertical line test. That's the key to understanding this problem. What conditions would assure that g has an inverse? In other words, the original, the red function, has to have a certain condition so that when you do its inverse, it's still a function. What would the inverse of this parabola be? Sideways parabola, not a function. So what does the original?
Pass the horizontal.
It has to pass a horizontal line. We've talked about that before when we did inverses, but to pass the vertical line test after you do the inverse, the original had to pass the horizontal line test. In other words, it can't go up and then come back down. It can't do that. Okay? So you had to first understand that. And that's probably where most everybody gets stuck. Okay? All right, now, in the future, we got something with an inverse function. That's one thing we got to be thinking about because they do throw inverse functions in there. Almost every one of the packets has something about an inverse somewhere. All right, so now we start looking at these, and then these will make a little more sense. So here's a condition for g that g prime is always less than 1. Well, what's that mean? What would that mean about g?
G's always.
Slope is always less than 1.
Slope's always less than 1. So what would that mean on the graph if the slope is always less than
The
1?
slope could be negative and positive, so that's not a good one.
That's not a good one right there because it could be It wouldn't be very steep, because it's less than 1, but it could get negative and then go steep. So it could go up, could go down, which is going to cause this problem. When we flip it, that's not going to be good. What about this one?
Always bigger than one that works.
G prime's always greater than 1.
That's good, right?
That's good, because that means it's always, G prime's always positive, so G's always
Increases.
going up. So if it's always going up, it would pass the horizontal line test. When we flip it, so I think B's going to be the one. Let's just go through these real quick. What's G double prime greater than 0 mean?
Concave up.
Always concave up. Well, we saw that's not a good deal. This would be always concave down. That's not a good deal. And just being continuous doesn't tell you anything. I mean, that's continuous. This red graph's continuous, and that wouldn't be good. So it's B. Okay? So that is
So it's,
why that one's true.
it has an inverse when the inverse passes the
When the
horizontal.
original passes.
When the original passes the horizontal, the flipped version, the inverse, will pass the vertical. And that actually has got a name. It's called a one-to-one function. A one-to-one function is one that's not only a function itself, but its inverse will be a function. And what that means is it's a function that passes the horizontal line test. That's called one-to-one. Okay. All right. Many functions are functions, but their inverses would not be functions, and that's why we limit. That's why, for example, the square root function is just the top half of a sideways parabola. So that way it passes the vertical line test. Okay, so we limit the original parabola, and the same thing with sine and arcsine. Okay, that's enough. We could do this all day long. 19? Even you, even I have something on 19. Well, 19's got to be just about rewriting it, doesn't it?
Yeah.
Yeah. It's really. Well, all right. Well, I appreciate the effort. I can reward that. This would be x to the first. That is with the cube root, which would be x to the third. So that makes that x to the 4/3. It's on the bottom, means it'd be negative 4/3. So the derivative would be 1/2 x to the negative 1/2 plus 4/3 x to the negative 7/3. I was looking for a 7/3 here. Okay, yeah, there's 1/2 x to the negative 1/2 plus 4/3 x to the negative 7. Okay. So I mean, I don't want to ridicule it because evidently I did that. Must have been second block ridiculed somebody. Now they're all afraid to ask or something. I don't know. But you guys, I guess it doesn't. All right, theorems. Let's talk about these. So I can't give. We can talk about that pi problem, and I can still give you some work done. All right, so we have just one tiny little theorem to talk about, and we're finished with our first half of calculus with derivatives, all the different things with derivatives. It is one of the more important results from derivatives from a mathematical standpoint, not really from an application standpoint, but really just from a mathematical theory standpoint. These three theorems are three of the important ones. That's why we talk about. We don't do a lot of theory in this class. We don't do a lot of proofs. In a college class, you probably would do a little more of that. They tend to like the theory part of things a little more. But these are worth studying here a little bit. Now, the extreme value theorem we already talked about says if f is continuous on the closed interval, then f has both a max and a min value somewhere on that interval. This pointed out why it's nice to have a continuous function. So you guys already wrote this one down, right? It's nice to know you have a continuous function because you know you have a max and a min on a closed interval. And then we talked about where you can find them, stuff like that. But there isn't really any work to do with one like this. We did answer some questions about it in the homework, and so on the quiz Wednesday, you'll want to be able to do that. Then we had the intermediate value theorem, which also said it's nice to know you have a continuous function because on a closed interval, if it's continuous, that function's got to hit all the different y values between the endpoints. And we worded it a little different than that, but when you state the theorem, you should state it like this if you're asked to state the theorem, which I told you you would be on Wednesday's quiz. But also you may refer to this theorem to answer some questions like you did in your homework. Like we talked about the roots. If you get a negative y value and a positive y value, you know somewhere in between there, it had to hit 0 because of the intermediate value theorem. All right, now, here's the mean value theorem. This is the last one, the MVT. And this is probably the more famous one of the bunch. The mean value theorem, and by mean we're talking average, right? The average value, the mean value. It says, suppose that f is continuous on the closed interval AB and it's differentiable on the open interval AB. Now we're going to spend some time talking about that first sentence here in a minute. Suppose f is continuous on the closed interval AB and differentiable on the open interval AB. Then there exists a number C on the open interval AB, which means C's got to be in between the endpoints, for which f prime of C equals, and you see the formula.
We have to memorize this one too.
Yes. So 3 of the questions on Wednesday. State the extreme value theorem, state the intermediate value theorem, state the mean value theorem. And I may not ask them in that order. So don't memorize them in order. Okay? Memorize them by their names. That's mean of me to do, but it is the mean value theorem. Okay. Anyway. Now, what's going on? Notice in this one we add the term differentiable. Now, we did talk about how differentiable, here, I give an example here. I'll put that back up in a second if you didn't get a copy. But differentiable is it's like square and rectangle. A square is always a rectangle, but a rectangle may not be a square. A differentiable function is always continuous, but a continuous one might not be differentiable. The 2 red graphs are continuous. No breaks or jumps or gaps, holes. But differentiable means it's also got to be smooth, no sharp points. The derivative has to exist everywhere. But if you know a function's differentiable, you know automatically it's continuous. You don't have to say it. Okay?
We have to say it when we state the theorem.
So that's why I wanted to talk about that. Because notice the intervals are different here.
So you have to.
So we have to. Here's why. Because for the mean value theorem to work, and I guess I better not do that there for the recording.
Oh, because there has to be
We have to have, the function has to be continuous on the closed interval. You have to have endpoints. But it doesn't have to be differentiable at the endpoints. It only has to be differentiable in between. So we can have a function that did this. Now you guys, we still haven't talked about what the mean value theorem is really saying, so this isn't going to make a lot of sense just yet. But we can have a function like this, where this was our A right here. Okay, this was point A, and this was point B right here. We can have a function like this, and the mean value theorem is still going to work. It has to be continuous and include the endpoints, but it only has to be differentiable in between the endpoints. So we have to have both parts. So when you state it, it has to be stated this way. Now, what does this say? What's this side? Slope between 2 points, and specifically the 2 endpoints, A and B. So this side of the equation, and it might be worth jotting down here, this is the slope between the endpoints. Now, another name for that is average rate of change. That's where this gets its name. Sometimes this is called the mean value theorem for derivatives, or the average value theorem for derivatives. Okay? Because that's called average rate of change. Now, what's this side? What's f prime of c?
There's a point that has the same.
That's right. This is the slope at a point c. And that's exactly what this is saying. This is saying that if you know the function is smooth in between, then there has to be some point in there that has the same slope as the slope between the endpoints. Now, the example on my picture would look something like this. Here's the slope between the endpoints. Doesn't it make sense that somewhere in there, there is a point that has that same exact slope? Because what's happening is if I start here and end up here, on a line like this, then it's going to go, if it goes down steeper than this line. At some point, it's got to come back to get there. And at some point, it's got to have that same slope. Now, the common sense way of saying this, a real life example, would be if I average 60 miles an hour between here and Gibbon, finish my sentence.
You had to be about 60.
At some point, you had to be going 60 miles per hour. If I average 60 miles per hour between here and Gibbon, at some point I had to be going 60 miles per hour, because assuming that traveling like that is a differentiable, nice, smooth situation. Now, that seems just like common sense, so why is it such an important thing? Well, we're going to do an example here in a second. But as far as working out problems, and we'll do a couple that you'll have to do on the quiz. I want to do one that's a more theory thing, but you're not going to have to do that on the quiz. But then I'll give you some like what would be on the quiz. The other real life example, and I think you have a story problem that's similar to this, so I probably shouldn't ruin it. Yeah, or you have a homework problem. Well, what the heck? Well, have you ever been on the interstates down in Kansas has them, the toll roads, where you go through a toll booth and you grab they give you a ticket usually, it's stamped with the time you went through and which exit you were at and whatever. And then you drive on the interstate, and then when you get off, you have to go through another one. And then they take your ticket and they scan it and they see how far you went, and you have to pay, maybe $1, $1.50, whatever. It's like a use tax. In other words, what they do is to pay for maintenance on the road, they figure, well, this way the people actually using the road are helping to pay for the repairs rather than just tax everybody in the state, whatever. So that's the idea behind toll roads. We don't really have them in Nebraska, but so theoretically, so if you got onto the interstate at a certain point and say it was noon and you got your ticket and you went 100 miles down the road and you handed in their ticket and they scanned it and it was 1 o'clock. What's that mean? You just went 100 miles in an hour, right? So theoretically, they could program their computer to not only charge you the $1.50, but they could hand you a speeding ticket for going 100. And and those toll booth operators are pretty smart people. They probably took calculus. And so they could say, hey, according to the mean value theorem, you just averaged 100 miles an hour. So at some point, you had to have been going 100 miles an hour. Here's your ticket. Probably more, but they know, according to the mean value theorem, they know you were going 100 at least one time, right? So I don't know that would happen. I haven't heard of that happening. But
Kind of like the ones in Denver, they have them set up so that they just scan your license plate, they send you the bill so you get the ticket.
you just go through it and they bill you.
Yeah.
Yeah.
They just bill you.
Well, speaking of speeding, they also have those kind of cameras that do that same thing. Yeah, where you go. What's that?
They have an app so you can tell where those cameras are.
Oh, that identifies those speeding cameras? Yeah, because you go through those speeding, and a lot of times they'll take your picture and they'll send you the thing with the picture.
Brother
And
saw our home address on it, so we got it, and he's just like, it's this ticked off look, like he was late for work or something. He's like, yeah, I was.
I was late for it, and they send you the speeding ticket in the mail or the bill or whatever, or the toll thing. Yeah, and they do have some of those. I know in the East Coast especially they have more of that stuff. All right, so that's me. So let's look at a kind of a theoretical example. I'd like you to write this down, but I'm not going to ask you one like this. This would be something in college you would definitely get into more, the theorem things. But I want to talk about why the mean value theorem is such an important theorem. It just seems like kind of an obvious thing, but what's important about it is it connects f prime with f. Now, do you remember something that we have done? It's a huge thing we've done, actually, where we talked about connections between f and f prime. Well, the chart, yeah, derivatives. The whole chart. And the chart is almost everything we've done. I mean, you talk about local max min and finding inflection points and all that stuff and then a lot of our optimization, those problems were based off that as well, was all about connections between f and f prime. Well, here we have an actual equation that connects f and f prime. And so mathematicians, theoretical mathematicians, love this then, when they can prove, not just assume. Now, when we did the chart, we just took it at face value. You guys just believe me. That makes sense. If f prime is positive, then f must be increasing. Yeah, because f prime's a slope. And if slope's positive, it's going up. Yeah, that makes sense. Well, a mathematician wouldn't be satisfied with that. They'd want to prove that statement. So we're going to do it. So here's the statement. If f prime is greater than 0 for all x in the closed interval AB, then f is increasing for all x in the interval AB. That is our statement. We have said it many times, not quite like that, but now we're being kind of technical and wanting to use some real mathematical theory. And this is what we've said. If f prime is positive for all x in the interval, then f is increasing. Now, we did get into some technicalities. We could say f prime greater than or equal to 0, because it could have a flat spot and still stay increasing. Okay? This doesn't work. Actually, the way we wrote it, if we flip it around, the converse would not work. If f is increasing, then f prime is always positive. That's not really true. We'd have to say greater than or equal to 0, because it could be 0, again, flat spot. But this way it would work. This is a true statement. If f prime is positive for all x in the interval, then f is increasing. Now, how would a mathematician prove this? Well, what they would do is they would start with the mean value theorem. They would start with this right here, because we know, and what they would say, let me write it down first. They would start by saying, according to the MVT, right, this is true. Now, before we move on, we should make sure, because the mean value theorem has a couple of conditions on it. What do you got to have? Closed interval, continuous on the closed interval, differentiable on the open interval. Is there anything that was said in here that tells me that that is true? I do have this closed interval. Do I know the function's continuous? I think this says it right here. It's never going to be undefined. Now, I suppose you could argue that you could have a jump, a break, where f would always be positive. No, but f prime wouldn't be. We're talking about f prime here, aren't we? Since the slope is always positive, yeah, at a break you would have the derivative undefined. So I think this does it. By saying that the derivative is positive all the time, you're saying that this is differentiable. And what did we just say about a function that's differentiable? It's continuous, guaranteed. If you know you have a square, you also have a rectangle. So we actually have more than we need here, because this function is differentiable even on the closed interval, which is fine. I know the theorem just says differentiable on the open interval. That just means that's all we need. It could be differentiable at the endpoints too, and that's a bonus. Okay? So by saying this, we're basically saying the function's differentiable, which means it's continuous, which means the mean value theorem works. Okay, so we're going to do that. Now, I'm going to multiply b minus a over to the left side. So I get f prime times b minus a equals f of b minus f of a. Now, what can you tell me about f prime of c? Remember, c is some point on the interior of a and b. What can you tell me in this problem about f prime of c? We know it's positive, because they told us that in the if part up here. What can you tell me about b minus a? Well, it's the endpoints. Why does b minus a have to be positive? Because b is the right endpoint. And actually, it doesn't even matter that f is increasing, because we're only talking about x values here. We're only talking about a and b. right? So the interval goes from A to B, and see, and we don't know F is increasing actually, that's what we're trying to prove. Yeah, we don't know it's increasing. So, but A and B, we know A is littler than B. A is littler than B because of our interval we set up. So therefore, B minus A is big, take away little, that's gotta be positive. So we know this side is positive.
B has to be great.
So then we know that F of B, so this side's gotta be positive. So F of B minus F of A has got to be greater than 0. It's got to be. If this side's positive and these two sides are equal, then this side's got to be positive. So F of B minus F of A has got to be greater than 0. Now let's add F of A over to the other side. So that means F of B's got to be greater than F of A. Now what are F of A and F of B again? The Y values at the endpoints. This tells me my right Y value is greater than my left Y value.
So that proves that.
It proves it's increasing. And now you might say, well, wait, that just proves that the endpoint is higher than the other one. But remember, this could be any interval for this function. So that means no matter what interval I pick, the right end is always going to be higher than the left end. So I can take a smaller interval, or bigger interval, whatever, no matter what I pick. Any two numbers I pick for any interval, if the slope is positive, then the right one is always going to be higher than the left one. Therefore, this alone, this says it right here, that F is increasing. So they would say, therefore, F is always increasing in the interval AB. Okay? So there you go. It was pretty simple, really, when you look at it. Just did this. We took a couple facts, and that shows it's always increasing. To a mathematician, that is a beautiful thing. Okay? That is a proof. To those of us that just take math classes, it was awful. But if you really like theory, that would be cool. Now, let's talk about just a simple type homework problem that we might have. Let's look at that sample one first, and let's see if that does it for us. If not, I've got another example we can do. What, sample 1 or 2? I can't remember.
2. Yep, 2.
Sample 2, problem 11. There could have been one in sample 1. I don't remember if there was. Or one of the parts of a free response, maybe. There it is. Now, sometimes we can run into a mean value theorem problem and not even know it. And anytime you run into a problem that talks about an average slope or a slope between endpoints, whatever, very oftentimes it is a mean value theorem. So this would be what one would look like. They give you a closed interval, and you'll have some homework, at least one. What are the values of C that satisfy the mean value theorem on this closed interval with this function? Well, we have a formula. I mean, one nice thing about the mean value theorem is there's something you can actually plug into. The intermediate value theorem a little bit. We did a problem where we had to find, the intermediate value theorem says, okay, on this function, if it's continuous, you've got to hit all these y values. Let y be a 5. We had a homework problem that said, let y be a 5. Show that the intermediate value theorem works. Well, what you do is you set the function equal to 5 and show that it has a point. It has an output of 5. And find where that is. And that's basically what you do. Well, the same thing is true here. We take the mean value theorem, and they want us to find what C will make this work. So where do you start? But this is your A and your B. So basically you plug those in. Basically it's find the slope between those endpoints. Right? And I think on the quiz you should show this setup. I know in your head you could probably do all this slope calculation. It's not hard. I think you ought to write this down because it's going to communicate to me you're using the mean value theorem. Okay? So I think you should write that. And then over here, I'll just put f prime again because we don't have anything for that just yet. But, okay, so what's f of 2? Well, 2 cubed is 8. Negative 1 cubed, negative 1. So 8 minus negative 1 would be 9 over 3, which is 3. Right? So that's f prime of c. So what do we do from there? They want us to find C. Yeah, we got to do the derivative. In other words, they want to know where does the derivative equal the slope between the endpoints. Well, the slope between the endpoints is 3, so where does 3x squared equal 3? Well, that'd be when x squared is 1, when x is plus or minus 1. Oh, here's another good one. Yeah, because I read you guys the answers already, right?
Yeah, but it's in
It's the key then is the interval. That's right.
It's in there.
Well, no,
It's the end.
because remember what we said about C?
Oh, it can't be done.
C has to be in the interior between A and B, right? I think if you go back and look at what you just wrote
No.
back here, there exists a number C on the open interval AB, which means it can't be at the end point. It can't be A or B. So C has to be an interior point. Okay? Now maybe we should have said that here. Maybe I should have wrote interior on this on my little notes here. F prime of C is a slope at an interior point, C. All right, so back to this question. We would throw out the -1 and we would say 1 only. Okay? That's good. I'd kind of forgotten that they did that. Well, I did an example in the other class where, because I'd forgotten about this. So there's another one the other class won't have done. Maybe. I'll try to remember them all. But I gave them one where it came out where one of the answers was totally not in the interval. So you had to throw it out for sure. But it can't be in an endpoint. It's got to be in the inside. Okay, so again, the picture that is typically shown, I didn't do a great, this is the picture you often see for mean value theorem. Got a nice differentiable function. Here's the slope between the endpoints. It seems pretty reasonable that you're going to have some points that are going to have that same slope. That if you have a nice smooth curve, you take the slope between your endpoints somewhere along there, could be more than one place, where you're going to have the same slope. Has to be. But you think about this, and then this is the other picture I drew here. Think about what happens if it's not differentiable. If you take a V-graph, and let's say A and B, let's say these were your two endpoints. Here's the slope between the endpoints. Is there any place that has that same slope? No. There's no place that has that slope. The only slopes on the V-graph are -1 and 1. So if it's not differentiable, you're going to lose that. It has to be smooth for that to happen with the slopes. Okay, and that's the mean value theorem. All right, so you've got some homework questions on section 4.8, or excuse me, 4.9. It'd be this line right here. Oh, I wanted to give you that, talk to you about that pipe problem, so we'll do that real quick. But if you want to jot this down. So 4.9, so just some problems with mean value theorem. So they're going to be a lot like the problems we had. You know, does the conclusion hold, and it's got to be continuous and it's got to be differentiable, and so if it's not, then the conclusion may or may not hold. If you don't get an A, then you may or may not get the car. But there's that, and then of course we got the take-home quiz we do tomorrow. We're going to talk about that pipe problem here in a second. Then we got Wednesday, we got our no calculator quiz, which is about the concepts of chapter 4, and we'll talk more about that tomorrow. And then Friday, Monday, midterm. Okay, so 1 through 5 odd, 8 through 11, 19, and 13. So, the pipe problem, let me pull that up.
Do we get like a movie break day after our midterm?
Let me think about that for a while. No.
We could watch.
No. Good Will Hunting is a great movie. Language would be quite inappropriate for high school. The TV version,
Yes,
Yeah,
send
we'll-
home some forms.
send over that is a really good movie.
What?
We'll see. I don't know. Let me see. Movie? Have you ever seen Stand and Deliver? That's a calculus movie. That's a pretty good one.
just a mental break, you know.
Some sort of
We
mental
watch
break.
basketball.
Yeah.
Basketball.
We can just pause it on the problem where it says that it doesn't exist and it's calculus.
Yeah, we'll see. No, we won't be watching Mean Girls, but, and we will not be watching Ted, yeah. Okay. So here's the picture that I posted online. I told you guys I would have up on the website, so if you used it or didn't use it, whatever. One of the hints that I would give you as far as just working it, and hopefully you figured out this much, but if not, this could be helpful then, I guess, is you had are you taking it from the 8 foot into the 4 foot, or? So this hallway is 8, and this one is 4? Okay. So you have something like that. Now there's all kinds of ways you could set this up. You could call the pipe P. You got this great big triangle here, so you could set up an equation because you could split this, and you could split this like so because you know that this, you wouldn't know what this value is, but you would know this is 8 across here, and you would know this is 4, and this would be an unknown, so that'd be like an X and a Y maybe. You'd have both an X and a Y in there. And so you need to somehow get those. Now, similar triangles, and somebody came in this morning was asking me, is similar triangles part of it? I think absolutely they could be. Now, it wouldn't have to be similar triangles. I think another thing that's true is these two angles would be equal here, right? Those are corresponding angles. As this pipe moves, as we turn the corner, this angle is going to change. And that's equal. So you could set up some SOHCAHTOA stuff with your two triangles here. Okay? And you could get it. I've seen people do this in terms of theta. Right? And so they do a right triangle here and a right triangle here, and they find their X and their Y in terms of theta, and they substitute those in to their pipe equation, whatever. But you're trying to find the longest pipe, right? So that's just set up and similar triangles, whatever, you can go from there on that. But here's the question I really have for you. Has anybody gotten to the point where you set something up and you went and you did all your stuff and you went to justify it and you were looking for a maximum pipe length and it came out a minimum? I knew Ryan did because he asked me and then I wouldn't help him. But that does happen. That does happen. All I told him was, well, you're on the right track and I'll tell you I'm not. But if that happened to you, you're on the right track. So what I want to do is talk to you about why your justification ends up being a minimum. Okay? Because they want the maximum pipe. Well, first of all, think about all the different types, all the different pipe lengths that you could carry through here. And you say minimum. Well, geez, I could have a pipe this long. Right? I could carry a pipe this long and make it through there. Right? So you want longer pipe. So they want the longest pipe that would fit. So the picture is what makes it the longest pipe that can fit. What is it about my picture that makes this describe the scenario that would give me the longest pipe that would fit? What's that? Well, not quite, no. In other words, if I take a pipe this long, and pretend we're doing this hallway here, because this is pretty wide, and I'm not sure if that one's quite wide. And we were taking a pipe, and I take a pipe this long, I'm going to make that turn. Now, first of all, we can't do this to it, right? We're carrying it horizontal. We can't lift it up, because if we do that, then we need count 3. Right? We need 3 dimensions.
Jump right in.
We need 3 dimensions. So we're going to carry the pipe horizontally. So we're carrying a pipe, we're going to make the turn. But if it's only this long, I mean, that's easy. So I can carry a longer pipe. And a longer pipe, and a longer pipe, until, at what point, what would make me not be able to make the turn? If it hits the wall, right? Yeah, if I run into the wall. So the longest pipe that I can make turn the corner is the pipe that's going to hit the wall here, right? Scrape along the wall here, and what else? And hit this corner, right? The longest pipe is the one that's going to take maximum use of my space, which means hit these corners. Now, in this pipe problem, we're ignoring, I don't know if I said it in there, the diameter of the pipe. Now, in real life, you wouldn't be able to ignore the diameter of the pipe. That would add another complicating factor into this, okay? So we're gonna ignore the diameter of the pipe because that would affect where it hits, right? All right, so that's what makes this a maximum. So just by drawing this picture, I've now set out to find the set of all pipes that can make this turn. And the one that can make the turn is the longest pipe that can make that turn because it's going to hit the wall at those places. Now, our pipe equation then for this picture, let's think about all the pipes that would touch at these three places. Well, let's say we're coming down the 400 hallway. So I have this pipe and I'm coming down the 400 hallway. Now, before I get to the turn, how long could that pipe be? As long as the 400 hallway, right? So I could have a pipe that would touch here and then touch here and then down here touch maybe clear down by Kicker's room, right? Or Mandernet's room or whatever. That'd be a really long pipe. But as I get closer to the turn, what has to happen? The pipe has to shorten to make the turn. And so somewhere in here, the pipe would have to be about this long. And then as I start to make the turn, I could have a pipe that touched here, touched way out there. So of all of those set of pipes, what's the one I'm looking for? I'm looking for the shortest of that group of pipes. That's why the pipe answer that you find in this problem should actually, when you go to justify it, actually be a minimum. Because you're finding the one that is out of all of these ones that turn the corner, that are touching at these places. But it's the longest pipe that can make the turn, right? Because we could have shorter ones that don't touch anywhere, but that would not be the same scenario. So it's an interesting problem from that standpoint of thinking your way through that. But when you do the actual mathematics of it, set up your pipe equation and so forth, it turns out in the justification to be minimum. If it does, you're on the right track. Now, one last thing. It gets to be pretty messy with square roots and stuff, especially if you do the Pythagorean theorem way. Now, if you do it in terms of theta, I'm not sure it's quite as messy, but it still might. So when you do that derivative, it gets quite messy. Just do it on your calculator and jot down what it gives you. One of the things it tells you in there is SIGN, I think.
Yeah.
Yeah, that's plus minus. That's a calculator's way of saying plus minus. Don't worry about it, just write it down. So when you write down your derivative, just write SIGN.
Do I have to write down that entire I ran out of room. So.
At least you let the really, it's not that long, is it?
No, I had another thing.
Oh,
on
you
the
were
right-hand
squeezing
side.
it?
I
You were
had my
squeezing.
extra information right next to
Oh, you were squeezing. So you get this derivative and set it equal to 0, but then you can solve. You can do a solve on your calculator and it solves it fine. But anyway, that's what's going on. Okay, so that's some stuff with the pipe. You have the rest of the time to work. If you want to, talk about your take home a little bit, I'm okay with that. I'd rather you don't just blatantly copy from each other, but explain. And I don't know why, if I did all that work, I'd want to just give that to somebody else. But whatever. Sell it now. A little money changing hands. At least you'd get credit for being smarter, right? Anyway.
$10.
I'll give you a nickel.
I'll give you $10 or you get it out. Or
Yeah. And Ryan did not get any extra help. How many times